What if you traveled through space at near light speed, and while decades passed on Earth, you aged only a few years? This is not fantasy. This is physics. In 1971, scientists transported atomic clocks eastward and westward on commercial aircraft, then compared them to stationary clocks on the ground. The results were stunning. The eastbound clock had slowed down, while the westbound clock had actually sped up. It proved that both velocity and gravity affect time itself. In other words, through relativistic time dilation, reaching a future beyond your own experience is possible in principle. However, it's a one-way trip to the future. But what about traveling to the past? Do the laws of physics permit it? Today, we explore the physics of time travel. From Einstein's time dilation to wormholes and closed timelike curves. And the most profound question of all: if time travel is possible, why aren't visitors from the future here? By the time you finish this video, your understanding of time itself will have fundamentally shifted. Chapter 1. Time is not absolute. Time is the most familiar yet most mysterious concept we know. Everyone feels the flow of time, from past to present to future. But what if time isn't absolute? What if the flow of time changes depending on the observer? Einstein's special theory of relativity, published in 1905, demonstrated exactly this. Time for a moving object slows down from the perspective of a stationary observer. And the closer you approach light speed, the more dramatic this effect becomes. This is not abstract theory. GPS satellites maintain accuracy by correcting for both special relativistic effects from velocity and general relativistic effects from gravitational differences. This is the twin paradox. One twin travels through space at near light speed and returns to Earth to find the other twin has aged. The traveling twin has barely aged at all. This is not a metaphor. This is physics. Through relativistic time dilation, travel to the future is possible in principle. Moreover, in recent years, gravitational wave observations and imaging around black holes continue to validate general relativity with high precision, even in strong gravitational fields. The discussion of time travel stands on this solid foundation of exploring possibilities and constraints. And here's where a crucial question emerges. If travel to the future is possible, is travel to the past also possible? Do the laws of physics permit it or forbid it? The relativity of time completely defies our intuition. Yet this is reality. So let's dig deeper into what this discovery means. Chapter 2. Can the door to the past open? If travel to the future is possible, the next question must be travel to the past. Is this mere fantasy or a possibility permitted by physics? Remarkably, Einstein's general theory of relativity does not completely forbid travel to the past. In 1949, mathematician Kurt Gödel discovered one solution to Einstein's equations. This was the rotating universe model. In this solution, space-time curves in a specific way, and temporal paths trace closed timelike curves. However, Gödel's solution assumes the special condition of a rotating universe and doesn't directly represent our universe. Still, Einstein himself was reportedly troubled by this discovery. Furthermore, in 1974, physicist Frank Tipler proposed the Tipler cylinder. If there existed an infinitely long, rapidly rotating cylinder, space-time around it would warp extremely. And by moving through that warped region, one could return to the past. But here's the problem. For a Tipler cylinder to function, infinite length is required, and creating one of finite size would require negative energy, making construction essentially impossible. Then, in 1988, physicist Kip Thorne theoretically examined time travel using wormholes. A wormhole is a tunnel connecting two points in space-time. According to Thorne's calculations, move one end of a wormhole at near light speed while keeping the other stationary. Time dilation then creates a temporal difference between the two ends. If a traversable, stable wormhole could be maintained through negative energy density, the temporal difference between endpoints could theoretically create a path toward the past. However, in quantum theory, negative energy cannot be produced without limit. There are thought to be strong constraints on quantity and duration. So stabilizing a wormhole remains a theoretical challenge. In other words, travel to the past is theoretically possible, But realization requires cosmic-scale technology and physics we don't yet understand. Moreover, in 2022, an experiment using Google's quantum computer successfully simulated wormhole behavior. Theory is gradually approaching real-world verification. But the most profound question is just beginning. If travel to the past is possible, what happens to causality? Let's venture into the greatest paradox that time travel creates. Chapter 3. The Wall of Causality. Assuming travel to the past is possible, a serious logical contradiction awaits. This is the grandfather paradox. If you traveled to the past and killed your grandfather when he was young, what would happen? Your father wouldn't be born. And you wouldn't be born. But if you were never born, you couldn't kill your grandfather. One interpretation is the many worlds interpretation. When you go back and kill your grandfather, a new parallel universe branches off. In that universe, you are not born. However, the original you doesn't disappear. This is logically consistent, but it requires the premise that countless parallel universes exist, and there's currently no way to verify that. Another interpretation is the self-consistency principle. The laws of physics do not permit events that contradict causality. In other words, even if you return to the past, whatever actions you take, the entire history somehow adjusts itself to remain self-consistent. Recent experiments using quantum computers have reported results showing that at the quantum level, interference with the past is repaired, and the butterfly effect doesn't occur. Perhaps modern science is beginning to support the self-consistency principle that history protects itself. Physicist Stephen Hawking proposed the chronology protection conjecture in 1991. He suggested without proof that quantum effects might destabilize the formation of time machines, preventing their realization. To protect history from historians, as it were. But this conjecture remains unproven. We don't yet have the answer. Think about this for a moment. If time travel is possible, why aren't visitors from the future here? If future humanity develops time travel technology, they should come to the past. Yet no one has seen them. This is a different kind of question. If time travel is possible, why is there no trace of time travelers? There are three possibilities. Time travel is impossible. Future visitors are here but unnoticed, or humanity perishes before developing time travel technology. Each answer carries profound implications. The paradoxes of time travel ask us about the nature of the universe and our own limitations. Now let's organize what this exploration has revealed. Chapter 4. The World Revealed. So today, we've explored deeply into the physics of time travel. What we've learned is the astonishing fact that time is not absolute, but changes depending on the observer. And while travel to the future is already possible, travel to the past has serious paradoxes waiting. Let me share the insights gained from today's exploration. First, time is not an absolute flow. As Einstein showed, time changes depending on the observer's state of motion. If you move at near light speed, time slows down. This is experimentally confirmed fact. Second, time travel to the future is already theoretically possible. As the twin paradox demonstrates, traveling at near light speed allows you to reach Earth's future. However, it's a one-way trip. Third, travel to the past is theoretically possible, but the wall of causality stands in the way. As the grandfather paradox shows, interference with the past creates logical contradictions. The universe may somehow be preventing this contradiction. These three insights fundamentally change our understanding of time itself. Time is far more flexible and complex than we think. The exploration of time travel asks us about the nature of the universe. What is causality? Does free will exist? And what is time? These questions are at the frontier of science, and the answers remain unseen. I find this deeply humbling. The universe transcends our understanding. Finally, I want to ask you, if time travel is possible, why aren't visitors from the future here? And if travel to the past becomes reality, do we have the right to change history? There are no answers to these questions yet, but continuing to ask moves us forward. The mystery of time is one of the deepest mysteries in the cosmos, and the exploration has only just begun. After watching this video, when you return to daily life, I want you to be aware of something. When you look at a clock, remember that the time its hands mark is not absolute but relative. The now you're experiencing might be the past for someone somewhere far away in the universe. When your understanding of time changes, how you see reality changes too. Your now is a unique moment with special meaning within the entire cosmos. Share your insights in the comments. Your questions become the force that drives this channel forward. Thank you for joining me on this intellectual journey to the very end. The concept of time is a profound mystery connected to our very existence. On this channel, we'll continue exploring the nature of the universe, consciousness, and existence. If you find excitement in thinking beyond established concepts, please subscribe. We'll meet again in the next exploration. Until next time.